then I can record. All right, fantastic. So we are talking about chemistry of the troposphere today, and that's where we are. So this is obviously really important. We talked a little bit about the stratosphere on Tuesday. So we're going a little bit lower, closer to where we exist, and the things that affect us. So we're going to talk about like pollution and greenhouse gases and stuff like that too. So, of course, I don't even have this plugged in. Thought I was ready. Chemistry of the troposphere. So there's a whole lot of pollutants in the troposphere. You guys probably know that. We're not in like a super big city where we have a lot of smog or anything like that, but smog is definitely a problem in large cities. And we're going to talk about what that comes from and stuff today. So there are pollutants that are basically because of human activity. And I would call those unnatural pollutants. These are ones that are due to human activity. And that's like, it's usually excess of the stuff. So like we've made too much excess SO2, carbon dioxide should be something that you're familiar with, carbon monoxide, nitrogen monoxide, and extra ozone, which actually might surprise you a little bit. So these are all unnatural pollutants. Now, some of them can be made naturally, but we've kind of made an excess of most of these here. Sorry, I just wanted to zoom in a little bit of most of these compounds. I'm going to talk about what they do to our environment today. So the first thing I'm going to talk about is sulfur and acid rain. I know you've all heard about acid rain. Obviously, acid rain is rain that is acidic, which can cause all kinds of problems. Now, acid rain would occur naturally and does occur naturally. We just kind of compound it with all the stuff that we do. So the natural sources of acid rain are sulfur from volcanoes. And you might think, well, volcanoes don't erupt all that often, but when they do, they release a lot of sulfur into the troposphere. So that's where a lot of natural sulfur and sulfuric acid and stuff comes from. It can also come from things like forest fires, and we're going to talk a little bit about what those release as well. So the main natural source of sulfur is from volcanoes. So we shouldn't have a ton in the atmosphere, but we, of course, combust just about everything we can find, and that also releases sulfur. So unnatural sources are us doing combustion of coal and oil. Now, not all coal and oil has a bunch of sulfur in it. If it's from different parts of the world, it might have more or less sulfur in it. And we've kind of tried to find some ways to remove that sulfur because when you burn it, the sulfur turns into sulfur dioxide in the atmosphere. So sulfur dioxide is really what causes the problems when you actually burn the sulfur. So I'm not actually going to write out the full chemical reactions that happen, but essentially when you have sulfur that gets combusted and turned into SO2, okay, that happens in volcanoes, that happens when we combust things, that happens in forest fires. That SO2 is going to react with oxygen in the air and oxidize into SO3. Okay, so how does this happen? This little arrow right here was oxidation in the air. And once it turns into SO3, then it's going to mix with water. Okay, mix with water, aka acid rain, right? And it turns into sulfuric acid. Okay, so sulfur dioxide is oxidized with oxygen, and then it mixes with water and we get sulfuric acid. So that's how we get acid rain. So if you're looking over at this picture, a lot of the pollutants, and we're going to talk about NO2 and CO2 also, but we're right now focusing on SO2. When it gets produced, of course, it goes upwards and it gets into the clouds. And then once it comes back down, that's how we get acid rain, which of course can destroy all kinds of plant life. So natural rain actually is a little bit acidic. Natural rain has a pH of about 5.5. Okay, there's a reason for that. It's about 5.5 because it does have carbonic acid in it. So where that comes from is CO2. So we know CO2 is a prevalent part of our atmosphere. CO2, when it's with water, turns into carbonic acid. So naturally, because of the CO2 in the air, rain is about a pH of 5.5. Now, when we start introducing sulfuric acid, that shouldn't be there. However, acid rain has a pH of about 4.0 or lower. And that's where our problems come from. So a pH of 1.5 might not seem like a lot, but that's like 150 times the amount of acid that it should have in it. So it does make a big difference, okay? So natural rain versus acid rain. So over time, of course, this affects the groundwater and the lakes and rivers and things like that. This one's from 2010. This was actually the most recent map like this that I could find. And you might not be able to see it very well if you printed it in black and white, but it's been a very common and consistent trend that the east side of the US is a lot more acidic than the west side, and that's just because of population density, right? We burn a lot more coal and oil over here than we do over here because of the people that exist. But if you're looking at the colors, there's some like red spots where some big cities are, and that says that's a pH of less than 4.1. So that for lakes and rivers and things is very acidic, because if you look at this pH levels for aquatic organisms, snails like to live at a pH of 6, clams are at 6, a lot of fish are at like 5.5. You start getting lower than that, they all start to die. Frogs can exist at a pH of 4. You go any lower and then even the frogs are gonna die. And then actually anything under 4, microorganisms can't exist under that. So microorganisms can't survive. And so some of these areas that are at like 4 point, let's see if I can find one. There's some like 4.8, 4.7. Yeah, that's probably the lowest one I can see. That's pretty tiny. But if it's at like 4.7, then the only things that are going to exist are perch, frogs, and those microorganisms. If we get too acidic, everything's going to die, because of course, if we don't have microorganisms, that's going to screw up the entire food chain. So acid rain over time can definitely be a problem. So we have started trying to combat that, and I'll talk about what we did in a second. So of course, acid rain over time lowers the pH of lakes, rivers, etc. Okay. Now, not only does it affect these organisms, it also destroys buildings. So any buildings that are made of stone and metal will react with that sulfuric acid in the acid rain. Okay, and then they start to degrade. This very commonly starts breaking down historic buildings, and there's a reason for that. So historic buildings are most affected. Excuse me. That's supposed to be an A. Okay. So historic buildings are actually affected a lot because they are generally made of stone or limestone. So historic buildings are made of limestone. Limestone is just calcium carbonate, and this reacts very readily with acids, or specifically sulfuric acid. Excuse me. So that starts to break down those buildings. Now, this specific reaction we actually started utilizing to try to fix the problem. So what we've done, I should have made a little thing for that. What we've done is we've tried to take out the sulfur from like the coal and oil before we burn it by using limestone. So we try to remove the sulfur. Hey, guys, in there, shoot, in there, go away. Okay, remove sulfur before burning by reacting with calcium carbonates. And so we can kind of control that. Guys, out. I am in the middle of class. Go away. I am so sorry. Go in there. You can play in there or upstairs. Shoot. Okay, so we kind of like utilize that reaction to kind of trap the sulfur before it gets burned into SO2. So that's kind of where sulfur comes into play. Notice when I was up here, I said something about NO2 and CO2. So I'm also going to talk about those here in a little bit. So before we do that, we are going to switch to carbon monoxide. So carbon monoxide is another issue in the atmosphere, and carbon monoxide is from incomplete combustion of hydrocarbons. So like we combust hydrocarbons in order to get fuel. The CO is a byproduct of that from incomplete combustion. incomplete combustion of hydrocarbons. Okay, and incomplete combustion, it just means that there's products other than water and carbon dioxide, because we always make water and carbon dioxide. It just means that there are other products besides CO2 and H2O. So like you can have some side reactions, you can have some of those breaking down when they interact with each other, but a lot of the times we make some carbon monoxide. So this is what happens if you run your car in your garage with the garage door closed, you get a lot of carbon monoxide, which is a problem because that can kill you. So CO obviously is bad for humans. We have carbon monoxide detectors in our house for this very reason. And I'm going to kind of talk about the reason why. So this is the Lewis dot structure for carbon monoxide. Okay, this is a triple bond, and we talked about how triple bonds are pretty stable and unreactive, and that's true. So this is fairly unreactive, but, and this is a huge but, these little electrons right here like to bond to stuff. Okay, so what they do, these like to bond to heme. This is heme, and that's in your blood, like hemoglobin. Okay, so what happens is, so this is a heme molecule. See the little iron there? So we've got iron in our blood. Oxygen is supposed to bond to heme. However, if there's too much carbon monoxide takes the place of the oxygen and your body can't circulate oxygen. So the problem is that heme has an affinity for carbon monoxide 210 times greater than oxygen. So if carbon monoxide is really abundant, it's going to attach to the heme instead of oxygen, and that's where those problems come in. So that's what will kill you, is essentially your blood not being able to circulate oxygen because it's circulating carbon monoxide instead. So that's essentially what will kill you. So you need to be really careful and keep your carbon monoxide detectors up to date. Okay. Now, if you are a smoker, which I highly do not recommend ever, but smoking and carbon monoxide, this is kind of part of the reason that smokers can't breathe as well. You might be coughing a lot. You can't circulate, your body doesn't circulate oxygen as well. And part of that reason is because what's going on is incomplete combustion and you're making carbon monoxide. So a non-smoker usually has 0.3 to 0.5 of these, this HB stands for hemoglobin, with carbon monoxides on it. Whereas a smoker usually has up to 4% of their hemoglobins have carbon monoxides on them. That's what that COHB stands for. So that's a really big difference. Okay, so the more carbon monoxide that you have attached to that heme means you have less oxygen attached to that heme. And over a long period of time, this can kill you. Okay, so if this is sustained, this high concentration is sustained over time, that can lead to death. Okay, so you don't want to obviously inhale a lot of carbon monoxide. All right, so that's carbon monoxide. We're going to move on to another pollutant in the atmosphere, and that is nitrogen oxides. And notice I didn't say like nitrogen monoxide or nitrogen dioxide. There's actually multiple molecules that are made of nitrogen and oxygen that are pollutants for us. So anything that's a nitrogen and oxygen compound. So I'm going to talk about smog, and I kind of mentioned this at the beginning of class. Smog doesn't necessarily affect us here in Bloomington Normal, but in larger cities, it can be a huge problem. It's a huge problem in China. It's like brown air. Okay, so smog is really made of brown compounds that are nitrogen oxide compounds. So these are brown compounds. And they're like N something, O something. Okay, there's multiple numbers. Now, usually the one that's brown and causes the air to go brown is nitrogen dioxide, but it can be NO, it can be N2O4. They all kind of exist in an equilibrium and cause a multitude of problems. So that's what smog is. Now, if we didn't have smog, so under normal conditions, we know most of our atmosphere is made of nitrogen and oxygen. So we're going to look at this reaction really quick. If it were going to react and make NO, that would be considered a nitrogen oxide. This reaction has a K value of 10 to the negative 15th. Notice this is a very small K value. That means this reaction really does not go to the right much at all at 300 Kelvin. And 300 Kelvin is like a little bit warmer than where we normally are at. But in general, this reaction like doesn't happen much at all. Okay. Now, however, when we have things like electric discharge or in automobile engines, the nitrogen and oxygen, will you shoot? Go away, you can have it, go away. Nitrogen and oxygen, this reaction is much more likely to happen because I want you to look at this. The K value is now 0.05. Now, it's not completely going to the right, but it's definitely making a lot more products than if K was 10 to the negative 15. So this is a larger K value as the temperature goes up. So essentially, if it gets that hot, and it does get that hot in automobile engines or when lightning strikes, you're much more likely for this reaction to happen. So we're going to make this NO, which is a problem. Okay, so is that all I wanted to say about there? Yeah, increased temperature if it's hot enough. That's the only thing that I want to write there. So the hotter it is, the more likely this is to occur. So more automobile combustion, more nitric oxide being produced. So when we have a bunch of this NO in the air, it can cause problems, but it also can react on its own. So a reaction the nitrogen oxide does, or nitrogen monoxide does, is it'll react with O2. So this is another reaction that can happen. So 2NO can react with oxygen. And this is how we get all of this brown stuff, this 2NO2. Okay, this K value is 10 to the 12th, which is huge. And that's at 300 Kelvin. Like that's at a normal temperature. So this reaction, so if I have a whole bunch of this reaction is definitely going to happen. And I'm going to make a bunch of NO2. Hey. Okay, so this reaction is very likely to happen. These are all based on your K value. So we have to understand what K value is in order to determine, guys, if a reaction is actually going to occur or not. Okay, hang on. Okay, so another reaction that can happen. So these are all possible reactions, right? So this is how we make NO. This is what NO does. We can also have photodissociation of NO2. So we talked about photodissociation on Tuesday. That's just like absorbing energy and breaking apart. Well, this can happen to NO2 as well. So NO2 can absorb some wavelength. And if that happens, it's going to break into nitric oxide and oxygen. Notice we already saw this guy, and that's pretty reactive. We can get a lot more NO2 back from that. But this should also kind of point out to you, we talked about little free oxygens on Tuesday and how they like to attach to O2s, and that's how we get ozone. So this actually makes more ozone. Now you might be like, well, that's a good thing, right? We want more ozone. Well, remember, we're in the troposphere. Ozone is supposed to be in the stratosphere. Okay, so if you look at this little graph here, the ozone layer, this is where we've got all of our ozone, and that's good. But if we go lower, we should not have that much ozone. But right now we kind of do have a decent amount of ozone, and that's because of this pollution that's going on.
Hello.
Hi.
Sorry I'm late. I was driving home from school. I wanted to leave before it got worse. So
that's fine. I'm recording this, so I'll post it later so you can go back if you need to.
Okay.
Okay. Great.
Got it.
Okay. So yeah, we're on page 6 of the ones that I posted online. So here are we. We got more ozone, which is great, but I was just talking about how ozone, when it's in the wrong spot in the troposphere instead of the stratosphere, it causes problems. Okay, so ozone as a pollutant. So this is true near the ground because it's so reactive. It's so reactive. So like ozone is great to protect us because it reacts with all those rays coming in from the sun, so that not as many of them get through. But we don't want all those reactions happening close to us because that's going to give off a lot of energy and it's going to break down oxygen that we need. So it's so reactive. So it's going to take up some of those O2s. And this really causes problems a lot of the time for people who have asthma and the elderly. So this causes problems for asthmatics and elderly. So if we don't have the right percentage of O2 in the air, we can't breathe very well. Joey, can you stop? I will watch it later. Stop. Okay, so NO making O3. We got problems with NO2, we got problems with NO, we got problems with ozone. But we kind of do have a fix for this. And you might know what this is. This is called a catalytic converter. You're required to have these in your car. And what they do is they convert these things that we don't want, these carbon monoxide, these hydrocarbons that are unreacted, these nitrogen oxides that we were just talking about, into things that are not so problematic. Now, CO2, yes, problematic, but it's better than carbon monoxide, and water and nitrogen. All of these things are pretty stable and normal for our atmosphere. So catalytic converters are hugely important in reducing things like smog. Okay, so these ones are much less problematic. Okay, and these reactions where it's like breaking them down are very important. Okay, so catalytic converters, huge help for reducing smog and pollutants in the atmosphere. Okay, so now I'm going to talk about greenhouse gases. So this is like a much more controversial and big topic, especially right now. So I really like talking about these because, and you might have questions, you might want to chat with me at some point. It's really interesting how greenhouse gases affect all of this. So it's a delicate balance in our atmosphere. And we're going to talk about all the molecules that kind of affect this whole global warming or global climate change, whichever you would like to call it, and what's really going on. So moving on from smog. So greenhouse gases, we've termed them greenhouse gases because they are the reason that it's keeping the heat in and the planet's warming up, just kind of like a greenhouse. So what's happening is these greenhouse gases, which are in the atmosphere, see these guys, greenhouse gases in the atmosphere, they absorb what's called long wave radiation. Okay, and this is like all the short waves were reacted and didn't get into the atmosphere, or if they did, we kind of like absorb them and we use them and things like that. The long wave radiation is the stuff that got through the atmosphere, but then it gets trapped. Okay, so long wave radiation then gets kind of absorbed because of the atmosphere. And when I say because of the atmosphere, I mean because of all the molecules in the atmosphere. Most planets don't have an atmosphere, or at least not much of an atmosphere like Earth does. We have a much more abundant atmosphere than Mars, for example. So before I kind of walk through this picture here, the reason that this whole radiation thing is causing us to heat up or to maintain temperature anyway, is because of those molecules. So on Mars, the temp actually drops like 100 degrees Kelvin or Celsius because they don't have an atmosphere or anything to absorb that heat. So Mars, the temp decreases by about 100 K. That's a lot at night because it doesn't have an atmosphere. It doesn't have molecules to absorb that radiation. At night, because no atmosphere. Okay, we need our atmosphere. It's very important to keep us warm. Obviously, if our temperatures dropped 100 degrees every night, we would have a lot of problems. So what's really going on? And I like this picture because it's numbered. It kind of walks you through what's going on with which light waves are getting through, how much energy is getting through. Now we're not going to calculate any of that. We're just kind of generally look at this, but essentially we've got like solar radiation, of course, coming from the sun. So that's step number one. The solar radiation is coming on into the earth from the sun, of course. Now, some of it gets absorbed because we've got clouds and stuff here. Okay. And that actually makes a big difference. Clouds can be extremely helpful. So the clouds absorb some. Clouds absorb some. So not all of it gets down to the earth. Okay, so that was like step 1 and step 2, some of it gets absorbed. Now, once it gets down here, okay, some of it doesn't get through the atmosphere. So if you look at number 3, some of the solar radiation is reflected by the atmosphere. Okay, so some of it, like it just can't get through those molecules. It doesn't cause a reaction or something. Sometimes it does cause a reaction, like we've talked about photodissociation and photoionization, but some of it just gets ejected back out. Okay. Now, if you go to number 4, solar energy is absorbed by the Earth's surface and warms it. Okay, this is kind of what we were talking about Mars-wise, and like we need our Earth to stay warm. So some of it gets absorbed down here. Okay. And then we've got number 5, some of the infrared radiation is absorbed and re-emitted by the greenhouse gas molecules. Okay. This is why greenhouse gases are important, but can cause more warming than what we want. So they absorb and then re-emit different wavelengths of molecules. Okay, so this is what we're going to talk about, this kind of step right here. Okay, now what also happens, some of the infrared radiation passes through the atmosphere and is lost to space. So some of it goes, some of it is gone, but a lot of it kind of stays down here. So you can see this arrow, some goes out, some stays down here. Some goes out, some stays down here. And then the surface ends up gaining more heat and infrared radiation is emitted again, and it's this whole cycle. Now it's an important cycle, like I said, but it's this whole cycle. Notice down here, he said when it's absorbed and emitted back, that's the long wave infrared radiation that we're talking about. So we're really talking about these steps over here, like 4, 5, and 6. Okay. And like I said, it's really complicated. This is a very delicate balance of what's happening in the atmosphere. So we're going to try to break it down as much as we can, but like what's going on with this absorption and re-emission of heat. Okay. So greenhouse gases, what are they? All of these right here are greenhouse gases, and you've probably heard of all of them. Of course, carbon dioxide, that's the one that everybody's like, this is so bad. We blame carbon dioxide because we've made a ton of carbon dioxide. Water, believe it or not, is also a greenhouse gas, like the water in the atmosphere, like water vapor, also absorbs and re-emits radiation. Methane, you might have heard of methane being an issue. Everybody talks about cows producing methane, and it's actually because they chew their cud so much that they produce a lot of methane. So beef, farmers who have beef and cattle actually produce a lot of that methane. Nitric oxide, we talked about where that comes from, and ozone, we talked about where that comes from. So all of these are greenhouse gases. Some of them are more abundant than others. So believe it or not, the one that is the biggest greenhouse gas, the one who does the most absorbing in radiation, is water. Water vapor actually does about 90% of the greenhouse gas reactions. Now, there's nothing we can do about the water. The water is going to be in the atmosphere. It's part of the air, and it's not because we're putting it there. It is natural. Okay, so this is actually our primary greenhouse gas. You might have thought it was carbon dioxide. It's not. Carbon dioxide is secondary, and methane is up there too. But we kind of attack carbon dioxide because, well, we're the ones producing carbon dioxide. We're not producing so much water that it's a problem. That's there anyway. So a lot of the time you see like this graph here that shows our CO2 emissions over the years. And yes, this is alarming, right? We've gone from the 1900s to when we started like the Industrial Revolution and all of that up to where we are now. Very, very high amounts of carbon dioxide. And you might have noticed it dipped a little bit because of the pandemic and people weren't going as many places, and that was natural to happen. But over the years, it's actually gone up about 35%, in the last 40 years. Okay, and this is because of humans, Okay, so carbon dioxide is a problem. I'm not saying that it's not. It's just not the biggest contributor to greenhouse gases. Okay, so what do these do? Why do these affect the temperature? If you look at the next page, they are absorbance spectrums for these greenhouse gases. Okay, so things that absorb and emit radiation. So I like this chart here. This is actually stuff that you would look at if you take like organic chemistry. You can see which types of waves are absorbed and emitted by which molecules. also inorganic and PChem. But the atmosphere, this is all the stuff that gets absorbed in our atmosphere. And then if you look at each individual graph, you can see which ways they tend to absorb. So I'm just going to look at water here for a minute, and you can see water absorbs a lot of waves down here. Okay, so water likes to absorb, these are the infrared waves. Okay, and it absorbs a lot. That's why it's the biggest contributor to greenhouse gases. So H2O absorbs, I'm going to put it the best because it absorbs a lot of those waves. Okay, carbon dioxide also, notice not as much, but also in the IR. Both of these absorb IR radiation. Now, if you're looking over here, you might have noticed this peak over here. Ozone tends to absorb UV radiation, which we also talked about on Tuesday. That's a good thing. We want it to absorb the UV radiation. So if you look at these graphs, you can kind of see which wavelengths are absorbed by which greenhouse gases, and they get absorbed and emitted, and that's how we kind of keep the energy where it is. Okay. Now I want to talk a little bit about how complex this is. So a lot of people will latch on and be like, well, CO2 is going up, temperature is going to go up, or it's going to die. But it's a very delicate balance of a lot of factors. So there's a lot of projections out there. Like I know we've all heard about global climate change and the Earth's temperature increasing. They, quote unquote, lots of climate scientists, they've predicted that our temperature could rise by possibly 3 degrees Celsius. That's a lot to get the temperature of our Earth to rise 3 degrees Celsius. That would actually melt all of the ice caps. So they predicted that it could rise about 3 degrees Celsius. They said by the end of the century. So we got a while. By the end of the century.
How long is that? How much is that in Fahrenheit?
I don't know. Somebody want to do that one for me? Let's see. 3 times. 37.4. No, that can't be right. That's not right. Alexa, how many degrees in Fahrenheit is 3 degrees Celsius?
3 degrees Celsius equals 37.4.
Oh, I was right. 37.4. So yeah, that's quite a bit. And like I said, that would melt the ice caps, and that would be obviously potentially bad because then we'd be underwater. Well, we wouldn't, but the other ends of the United States would. So yeah, that's a lot. Now that's a very high prediction, and that's based on just the things that make the temperature go up. Now, there are also things that make the temperature go down. Like I said, this is a delicate balance. We don't really know 100% what's going to happen until it happens, unfortunately, because as the temperature increases, it changes the weather. So we also get increased cloud cover. And when we have more cloud cover, then we don't have as much radiation coming all the way through. So that would be something that counterbalances the temperature going up because of greenhouse gases. Okay. Another thing is that the carbon dioxide relationship, a lot of people compare, right, that carbon dioxide increasing relationship to the temperature increasing relationship. And they say that it's exponential. And if you actually look at the numbers, it's more of a logarithmic relationship. Okay, so more logarithmic with temperature. Okay, not exponential. Okay, so what I'm really getting at is all of these things and more. It's a delicate balance. Okay, there's a lot of moving parts. And yes, climate scientists do take all of these things into consideration, but it's really hard to predict when you have all of these things changing. Yeah, I think you're right, Troy. It was just saying the straight temperature, the temperature change is going to be different. Yeah, that's not going to be 37. 5 sounds about right. Thank you. So yeah, yes, carbon dioxide increasing is a huge problem and one that we can work on controlling. But like I said, there's so many things going on. It's really hard to predict what's going on or what will happen. So we've seen a lot of predictions, temperature going up, all of those things. You kind of have to take them with a grain of salt because there are so many things happening that, like I said, it could increase cloud cover and then we won't have as much, as many rays coming through, that type of thing. So other forces that drive climate change, and actually the main forces that drive climate change are going to be the sun and the ocean, which of course covers most of our world. So the sun, you probably already know this, that it has cycles, right? It has cycles of sunspots. So it actually produces different amounts of energy at different times of the year. So its energy output varies. Every 11 years with sunspot activity. That's what this graph is of. I know I cut off the axes in the title, sorry about that. But that's essentially what's happening is we get peaks and valleys of how much energy is coming from the sun. So that drives climate change as well. And the ocean cycles drive climate change. So oceans, different parts of the ocean change temperature a lot. You've probably heard of El Nino. When we're in an El Nino year or a La Nina year, the temperatures change quite a bit, the winds change quite a bit, and so does the climate. So in the ocean, La Nina and El Nino affect the ocean temps. And honestly, so does ocean acidification, which I'm not even really going to talk about today, but that can cause problems as well. So we can actually predict the weather a lot more based on these specific cycles than what's going on with carbon dioxide and all of the greenhouse gases. So these are actually better predictors for precipitation. So we use these to predict precipitation, temperature, hurricane frequency. All of these things are affected in our fun, delicate balance that is our world. I'm going to move on to the oceans here. So once you guys get this down, I'm going to scroll.
So I actually looked it up when you did the Celsius thing, the 3 degrees Celsius.
Yeah, what is it?
So I looked up the average Earth temperature as of 2011. I guess it was 14.4 degrees Fahrenheit.
Right.
And an increase to about 17 Celsius would mean about a 5.4 degree Fahrenheit change.
Yes. So that's how much it has changed.
That's how much it's estimated to change by the end of the century.
Oh, to change by end of century. Awesome. Thank you.
Yeah.
Yeah. So what I asked Alexa, it told me what that temperature was in Celsius.
Right. That I realized that. I thought
sorry
37 was really high.
That would be insane. Yes. So I appreciate that. Thank you.
Yep.
Yeah. So 5 degrees may not sound like much, right? But that would be enough to melt the ice caps and cause all kinds of problems. So thank you for looking that up. I appreciate it. Okay, so on to the ocean and fresh water. We're almost done. Okay, so we obviously know that water is really important. Water is really important in chemistry because we do almost all of our reactions in water because it has very special properties. So you guys know all of these things. We're just going to kind of like put them on here. Okay, water, whether you believe it or not, actually for its molecule size has a very high melting point and a very high boiling point. So it has a high melting point and boiling point for its relative size. Okay, and that is because of those hydrogen bonds, of course. Okay, it's got hydrogen bonds. Those are really hard to overcome and to get it to spread out. Okay, so those hydrogen bonds really kind of drive life on Earth. So it's got a high melting point and a high boiling point. It's got a high specific heat. It's hard to change the temperature. High specific heat. Right, 4.18 joules per gram degree Celsius is a lot higher than like metals. Metals are almost always less than 1. Most substances are somewhere around 1, between 1 and 2, but water is 4.184. So it takes a lot of energy to change the temperature of water. Okay, it's also, and this is atypical, its solid is less dense than its liquid. Solid is less dense than liquid. And that's why ice floats. Most things, as they become solid, everything gets closer together and it's more dense. And that is not the case for water. And it is also very polar. That's why chemists like it, because it can dissolve all of those polar and ionic things. Okay. So these are the kind of properties that are really important for us on Earth. If it didn't have a high melting and boiling point, it wouldn't stay liquid most of the time and we wouldn't be able to drink it. And that's the problem on a lot of other planets, is that it's not at the right temperature. So like it's a very special compound. So water on Earth covers 72% of Earth's surface. Okay, so that's most of it, right? But only a little bit of it is actually fresh water. 97.2% of that water is found in the oceans. Okay. Of course, most of it's in the ocean, some of it's in lakes and rivers and that types of things. So our fresh water that we of course need to survive only comes from streams, lakes, and groundwater. And that's where we get our fresh water, unless we distill ocean water, which takes a lot of energy. Now, these sources are very limited in some places, not where we are, but places like California, Nevada, Arizona, they can absolutely have water shortages or freshwater shortages, which can cause lots of problems politically and ethically. So we do have to be careful with our freshwater sources, and hopefully we can find a better way to purify ocean water, because then we would have more resources for water. So ocean water, then, if we did want to try to purify it, this is the problem. Ocean water has a lot of salt in it. Of course, it is salt water. It has lots of ionic compounds. So it's about 35 grams of dry salt per kilogram of water. To kind of like put that in perspective, that's a lot of salt. Okay, so in order to actually purify it, it's going to be difficult to get. So like this is our representation. So this was the water. If we can get all of this salt out, then we would have nice pure water. Now, what is in that 35 grams? It's not all NaCl. Of course, a lot of it is. So we've got sodium, we've got chloride ions. There's some sulfate ions, magnesium, 2+, calcium, and potassium. And most of those are kind of listed over here, but these are what we're going to find most of in the water. So we can actually use these if we do purify it. The commercially obtained substances from ocean water that we generally use are, of course, salt, regular salt. We can also get bromine from it, and then we can use the magnesium if we can get it out of the water and then reduce it. Yes. Okay, so how do we do that? There's a couple different ways to do that. One is, of course, we could like heat it up and collect it, right? That's called distillation, because it would leave all the salt here. It would put all the water over here. So we could distill it. Still. The other thing we could do is, and you might have heard of this, this is very common right now, is reverse osmosis. It's getting it to like filter kind of in a specific way. So if we distill it or reverse osmosis, both of these are pretty expensive in order to do on that large of a scale. But if we can, we could probably get some more water out of it. So I'm going to switch gears now to fresh water then. The fresh water that we do have, an average person uses about 300 liters a day, or that's like 80 gallons a day for consumption and hygiene. I'm like, that sounds pretty accurate if I take a shower and cook and use the bathroom and all of those things. So that's about how much water that we use a day. Now, of course, agriculture and industry use way more than that of our fresh water. So agriculture, of course, is extremely important, as is industry. But if there's a way to kind of cycle that back, that would be really great. So this is where our fresh water actually comes from, the water cycle that you learned about probably in like middle school. That's how we get all our fresh water cycle. That's this guy. No, I'm not going to ask you questions specifically about the water cycle, but I really just want to reiterate that freshwater is an important natural resource. Sometimes that we take for granted. And hopefully we can find some ways to maybe purify ocean water. So we've got some more fresh water. Excuse me. Okay, so oxygen in the water is the next thing that I want to talk about. So dissolved oxygen in water. So this picture, which is kind of hard to see in black and white, is essentially like a zoomed in portion of the water cycle. We've got runoff going back into the water. And what I want to look at or talk about now is the amount of oxygen in the water. So there's like O2 down here. We can get things like algal blooms, which can cause eutrophication, which is like death of everything. And so this is also a very delicate balance, just like the climate, the water itself is. So the oxygen in there, what we need is of course dissolved oxygen, because there's animals and things that live in the ocean, they need oxygen as well. So life in the water depends on dissolved O2. Okay, and water at 20 degrees Celsius, which is a pretty typical temperature. So 20 degrees Celsius, it can hold about 9 parts per million of oxygen. Okay, so that's not a lot, but it is enough to sustain life. Fish need about 5 parts per million. Now, fish need about 5 parts per million. Okay, so as the temperature of the ocean increases, that also causes oxygen not to be as dissolved, which can cause fish to die. But they do need about 5 parts per million. Now, the fish kind of battle it out with algae and bacteria who also need oxygen. And that's where we can have some issues occur. So bacteria and algae also compete for O2. Okay. So when we have bacteria and algae that kind of like get a little bit too excited and reproductive and they make lots and lots more algae, we get these things called algal blooms, and they cause eutrophication. So eutrophication happens when we have like too many nitrates and phosphates. It just kind of promotes algae growth. So this is spurred by nitrates and phosphates. Okay, and we haven't talked about nitrates and phosphates today specifically, but those can come from pollution as well. So the more polluted the water is, we might kind of cause more algae and bacteria in the water to grow, which negatively impacts the wildlife that we want, like fish. So there's actually some spots where this like consistently happens. This is right under Louisiana. Okay, this is the Louisiana shelf. And the oxygen levels are very low here. So the fish cannot exist. So this is wide scale eutrophication. So eutrophication is death of all plants and fish. Okay, and this actually happens when rivers are emptying into the oceans, which is why we see it down here where there's multiple rivers that empty into the ocean. So happens where rivers empty into oceans.
So wait, in that like whole area, there's like no fish at all?
Yeah, so it's kind of a little bit further off coast than like what it seems here. But it's the bottom oxygen. So there might be some on top, like some fish closer to the surface. But closer to the bottom of the ocean, we've got like nothing going on down there. Excuse me. Yeah, if you look at these numbers, as it gets red, that's less than 2 parts per million of oxygen. That's not enough to sustain anything. So we'll get all that algae and bacteria, but that's about it. Okay, so onto water that we drink, and that is municipal water. Water in our homes originates, and I already mentioned this earlier, this comes from lakes and streams and groundwater, lakes, streams, and another word for groundwater are aquifers, so underground aquifers. We actually sit on top of, or pretty close to, on top of a very large aquifer, and that's where we get a lot of our water. My hometown is like right over one of the biggest aquifers in the Midwest, which is kind of cool. But that's where we get a lot of our drinking water. Now, of course, it's a very complicated process to get it so that we can drink it. This has always been kind of interesting to me. My dad actually works as an engineer and has goes to lagoons and stuff to check on how the water is doing. But if you look through here, this is kind of the process by which the water gets to where we can have it. It's very complicated. They've got to filter out coarse stuff, right? And then sedimentation of smaller particles, that would be getting smaller particles out. And then sand filtration gets out even smaller things. And then we have to aerate it and sterilize it with chlorine. So chlorine can also be an issue when we're looking at things like runoff and pollution and that. So we have to be careful. But you don't have to be able to describe the whole water treatment process. Okay, and this is the very last thing that I want to say on the topic of chemistry of the environment, and that's about green chemistry, and which really has nothing to do with everything that we've been talking about. So green chemistry is really important for people who work in labs. This is something that I think about when I work on editing our labs, because we use some materials and chemicals that are really not very green, and we could do the same experiment with chemicals that are better for the environment. So this is kind of like our guide that we should be looking at. Things that as a teacher, I can focus on are like preventing waste and using less hazardous synthesis. But these are all things that as you go into the field, you will be looking at, because there really is a push for green chemistry now. And hopefully we can kind of bring down that level of toxic things. So we want to be as least hazardous as possible. And most chemists do try to think about this. I kind of like this because it's kind of our, like it says, it's our guide, green chemistry pocket guide. But the goal is to have renewable and biodegradable materials and use catalysts and biocatalysts to improve efficiency. So if we can make systems that are more efficient, use less product, that's always the goal. And like I said, most chemists actually do think about this. And this is something that I'm trying to do even for our lab that's pretty small. So I honestly feel like some of this, and I'm going to stop